Hello and welcome back to Calculus 2, the section on Introduction to Differential Equations. There are courses upon courses upon courses and courses branching out of the field of differential equations. Differential equations in terms of technical fields, economics and so on is probably the most important part of mathematics. Every single formula in physics came from some sort of differential equations in one way or another. And if you know differential equations very well, much of physics makes sense very quickly, and you don't have to remember many of the formulas because you can derive them at any time. We will go over some very simple stuff today as the introduction, but the most important is to define what the differential equations are and to talk about their solutions and see how to check basic equations. The first differential equations course that we teach here at the college is transferable to Rutgers and NGIT and MIT and so on. It's the same course. And then after that course, it branches into the whole spiel of other courses, such as partial differential equations, dynamical systems, and so on. Yes?
Calc 4 above or beneath separated?
Well, in some schools, that is what's called Calc 4.
Oh, that is.
Yes, but some courses will, some schools will actually have the basic analysis course, Introduction to Mathematical Analysis, as Calc 4. Some schools call that Advanced Calculus. Some schools call it Intro to Analysis. Some schools call it Calculus 4. And some schools actually call differential equations Calc 4. So first I want to see is, yay, live stream is okay, because we don't have the issues with resolution. Good. So what is a differential equation? Differential equation is the equation which contains independent variable, function, and its derivatives. So any equation that has, let me just say, differential equation is an equation which contains independent variable, function, and its derivatives. You can have first derivative, second derivative, eighth derivative. That will determine the order of the differential equation. So we are going to write this as some function of, let's say, x, y, y prime, y double prime, y triple prime if need be, and so on, equal to 0. This is that explicit form to write functions. This is used much more in Calc 3 as a notation, but so it's a sum function of x, y, y prime, and so on. To give you an example of these differential equations, I will write xy double prime plus 3y is equal to sine x. So an equation like this would be called a second order linear differential equation with and non-homogeneous as well, because you have a forcing term on the other side. But this is the second order ODE, ordinary differential equation, because you have partial differential equations. And it's a second order because of the second derivative. We have, let's say, y prime, let's say, minus x squared y equals to 0, right? This would be first order linear differential equation, so I'll call this first order.
Yeah, what's ODE?
Ordinary differential equation.
That's a G. Oh, G.
Here, ugly E for you, so you don't wonder. So differential equations are equations that contain independent variable, function, and its derivatives. The highest derivative you have will be the order of differential equation. Therefore, you see a second order and the first order because it follows the derivatives they have. Now, there are many methods to solve differential equation, and this field is vast. There are also numerical methods to solve it and so on. We have the course on differential equations, and that doesn't cover even the 10% of 1% of what's out there. It's just, to kind of get you familiar with mathematics a little bit. Differential equation still falls under basic mathematics or elementary mathematics in the eyes of technical schools like, NGIT, MIT, Virginia Tech, right? These schools. So that's that, elementary mathematics ends with differential equations, I would say. Now, what is the purpose of these equations? Well, as you observe nature, you observe that certain systems change in time, and you write that down as an equation, and we know that change is the derivative, and then what you get is the differential equation. So if I say that change of population in time is proportional to population, I verbalized differential equation, because change of population in time is going to be dp dt. The word is equal sign, proportional is some constant of proportionality k, and then times the population p. Now this formulation makes sense because the change in population will be proportional to the population that exists. See, thinking about the change of population in terms of, let's say you have only male in population, no female, that population will have to eventually die out because there will be no new units produced in that population because no female. The same thing would be if there is no male, right? So if you're looking at this, in that case, in both of those cases, this k would be 0. The constant of proportionality. You would have, let's say you have 200 females, right, and no male. In that case, population will not change. Well, eventually all those females would die of old age, but let's say these are immortal females, right, like elves, right? Well, in that case, you don't even care about changing population because they're immortal. Yeah, but you get the idea, right? So taking a look at this, what we have now is what we call a differential equation. Now, we have to understand, so let me just put here that, so this is the definition, right? That's important to understand what differential equation is. Now I'm going to write here, solution of differential equation is a function. Solution to the differential equation is a function. You are used to numbers being answers or solutions two equations, right? You have x plus 2 equals 5, x equals 3 is a solution. You have sine x equals to 1/2, so that x was pi over 6, right? So you are used to all of your equations so far had one or multiple numbers as a solution, right? X squared minus 1 equal to 0 had positive and negative 1 as a solution. So now this is like going a next step up. The solution to differential equation is a function which can generate numbers later. So now let's take a look. The basic way to solve differential equations when possible is a method of separation of variables. You have, separation of variables. This is the most basic way to solve. Very few differential equations solve this way, right? Just a particular form. But we use separation of variables, and you have two types of variables now. Here is in purple, population variable, and in red, time as a variable as well. So now, if I am to use separation of variables, clearly I should get all the variables of one kind on one side and all of the variables of the other kind on the other side of equal sign, thus separating them. This cannot be achieved every time, but in this case, dp over p is equal to kt. I was able to put all of the p variables on the left and all of the, k dt, I'm sorry, k dt. All of the variables. So this is essentially the differential thing, if you remember, from your Calc 1, right? And now we integrate both sides. Now one side is integrated in terms of p, the other side is integrated in terms of t. So those are two separate worlds, two separate integrals that are linked with equal sign that will link them eventually. What is the integral of dp over p? Excellent. Now I'm going to avoid plus c. I will put it on the other side. We need only one plus c per problem. And how about on the other side? kt plus c. So we are going to use plus c only on one side. We can have plus c1 plus c2, and then if you are to move c1, you can define c2 minus c1 to be a capital C, all right? So I can only have one c. I don't have to have on both sides. Cool. Now, I want to solve for population, right? So how would I do that? E both sides, very good. If I e both sides, I will get that population is equal to e to the kt plus c. Now that will further be e to the kt times e to the c. Now we agree that this over here is constant. I can call it anything. Call it capital A. I don't care. So population in time is a e to the kt. This is your solution of the problem. You got a function in terms of independent variable t, which models population according to the sentence you had at the beginning. And this is how all of the physics and everything else started. This is what Newton figured out. So from this point on, you are going to have just crazier equations with crazier methods of solving it. But everything starts with observation in nature that something changes according to something. You write it as a differential equation, and then you figure out how to solve it, giving you a model, which is a solution, that models the particular phenomenon you observed. Observe what happens now. If I start with 200 females as the population, and k equals 0 because there are no males, so no reproduction can happen, 0 times whatever time you wait is e to the 0, which is 1. Your population is just those females, because the whole thing over here is just 1, right? Or put male, I don't care. However, if you have the balance in between, male and female, then this k becomes non-zero number. Give some time, population is going to grow because the graph for exponential function looks like this. This is your starting point A, which is the mix of male and female. And how steep this goes up depends on the k over here, which is the rate of growth, because the ratio male to female could be off. So the population definitely depends on the ratio between male and female, and that is captured with k in that case. So the more favorable ratio will have a higher value of k, and then that would result in the higher rise in population. All of that from a statement that change of population is proportional to population. Now, we start with this, understand this, then look at the graph and say, well, this is just a bad model, because looking in here, if you wait infinitely long, you will have infinite population, right? But we know that we can't wait infinite long because we all have expiration date, right? So maybe I want to subtract deaths, right? So there's going to be another function. So it's kp and then minus dt, d, right, of t, minus d, the number of deaths. And then you say, okay, so now I have to subtract this model and this part and this part. So you have to, and then you get into predator-prey models and all of these kind of things, and you figure out a lot of different models for population. This is the worst one of all, right? It's good on a short run. So if you want to estimate the population in like next 10 years, having the current state and 10 years ago, this model should do well, all right? Because on average birth and death happens, and it's just fine. You can go to the population clock. So let's go real quick and realize that there are differential equations that are driving this this thing. So here's the population clock, and this whole thing is driven by differential equations, which is computed real time. Like no one's going every second calculating these numbers, all right? This is the best estimate we can get looking at the differential equations which provide these numbers. So you see that we are almost at 7.4 billion. This is the population of the United States. You have the population of 10 countries with the highest population in the world right now. And for me, it's always interesting to see Japan in number 10, because I have no clue how they fit that there. It's just amazing. Of course, China, of course, India, of course, United States, of course, Indonesia with 1,000 islands, of course, Brazil, right, which takes almost all of the South America. Pakistan is pretty big. Nigeria was kind of surprise to me. Bangladesh, not surprised at all. Russia, definitely not surprising. But Japan was holy nightmare, really, right? Germany is about 90 million, right? So it's big. Yes. It's very small.
Not just that, but that's a lot of people. It's just a lot of.
No, but when you look at the volcanic, areas where you can't live, and you look at the mountains and things where you can't live, it's just, it's disproportional to anything else.
Not just that, but like within the last couple decades, the amount of people being born has dropped just drastically.
Yeah.
I think the reason they have such a high population is because
robots. They count robots.
No,
I was kidding.
That's the older generation, but once that generation dies off, then I feel like it'll drop a bit, but won't really pick up unless they solve whatever.
Oh.
Well, it's certainly a societal issue. Well, the problem is a big chunk of Japan's population is the older generation, and there's certain areas.
All right. So let's take a look at more differential equations. So we saw population clock, and we understand that this can be solved that way. All right. So now let's, since many of you are taking physics and you love it, many of you will be taking physics and you will love it. Let's, guys, physics is extremely important. I want to hear it. Learn mathematics, physics will be joke. Let's go. So let's take a look at more differential equations that are solved by this basic method. So let's do the experiment right now in the class. Behold the bottle. And all I'm going to do now is and it falls down, right? Falls down with what acceleration? Negative 9.81, which is gravity, acceleration of gravity. Now, the number in feet per second squared will be 32.2. Great. So how about if we just settle down and say g, because we can then use any units, we don't care. So let's say that acceleration is equal to just g. You want to use negative g, right? Because, right. Now, what is acceleration? I need specific words around. Nicholas first. And not what I was looking for. Those are units. I asked what is as a concept, yes? Nope. That one. What was that one? Change of velocity in time. Guys, you have two pedals in your car. One is gas, one is brake. They're both acceleration. Well, one is deceleration, but they both change your velocity, right? So, I'm going to rebrand this acceleration into change in velocity in time is equal to this, negative g. So we understand that acceleration is a change of velocity in time. The sooner you marry words and reality to mathematics, the sooner the physics is born and natural for everyone. So acceleration is a change of velocity in time. So now I'm replacing my acceleration a with dv dt, which is the change of velocity in time. Hit it with separation of variables. dv is equal to negative g dt. Hit both sides by integration. Now g is a constant, so I can put integration anywhere. G is a constant, I can just leave it outside of the integral. It's like k before. So now what's the integral of dv? And what's the integral of dt? And then we have plus some constant c. Now that c is, when time is 0, what? Initial velocity, you see that? So if at the beginning of motion time was 0, I didn't start yet, right? So at that point, when t is equal to 0, which is initial time, velocity is just c. So I can call this c initial velocity v0, and look what I got. Well, let me write it actually is math way. You will recognize this formula from your physics class if you're taking physics, as velocity final is velocity initial plus acceleration times time. Because that g is acceleration, and I have a minus there because it's falling. But I can have that any acceleration, right? So here is your acceleration equation. Now let's talk units just for a tag. The units for velocity are miles per hour or feet per second, right? Or meters per second. Let's do meters per second. And then gravity would be meters per second squared, and then time is just second, and that kills one of these. And you have still meters per second, and look, meters per second equals to meters per second plus meters per second. They have to balance that way every time. If you learn how to balance these units, suddenly physics and chemistry both become a joke, because you will never be able to write a nonsense equation because you see that the units don't work out. They have to balance throughout the entire equation. That goes for every equation without exception across all of those sciences. So meters per second for velocity, meters per second squared from acceleration, but then you have times t, which kills that square. And then you have meters per second. So now everything is meters per second. All right, so that's a little bit of dimensions, units. Cool. So we got this equation, we're happy. But now I have a next question. What is concept of velocity? I need better words.
It's how fast something goes. Displacement over time.
Change in displacement over time. See, in order for me to get to that door, I have to change my position because I'm here, door is there. It's going to take me time to get there. So, you can do, what do you want to do for distance? You want to do x or y, or let's do y, because we're talking about falling object, so it's covering the y distance, okay? So now I'm going to say that velocity is change in distance in time. As soon as you say to me change, I'm going derivative. And here I am facing another differential equation. So now this differential equation here, we separate variables again. So I have dy stays alone. On the other side, negative gt plus v0, everything times dt. And immediately, boom, integral. What's the integral of y? Of dy?